Welcome to the Pipeline Whiteboard Edition. Today, we're going to talk about asynchronous execution, one of the 4 key innovations that Monad introduces. Remember, it's a combination of many different optimizations that yield a system so performant it can produce 10,000 transactions per second at sub-cent gas fees. You're probably wondering, what's the impact of asynchronous execution? On a fundamental level, the block sizes can be much bigger than without it. Ultimately, this enables app developers to write much more secure code without being worried about increasing gas costs. For the end user, this leads to much cheaper and faster transactions. With expanded gas limits, Monad opens up brand new design spaces, allowing devs to leverage cutting-edge primitives such as proof verification and signature aggregation. Let's dig into the how and why with Zen Lama, who leads developer relations here at Monad.
So to start, we're going to give you a little bit of background just on like how you actually send a transaction to a blockchain to pull this all together. So typically when you do interact with a blockchain, say your wallet, it interacts with something called like an RPC server. So you usually send a transaction through that, which gets sent to, a set of validators that maintain something you've probably heard of called the mempool. So these transactions, they come in here, they sit here, and then one of these guys decides that he gets to be the leader at some point in time. And so he takes these transactions and he builds a block and he says, okay, I'm gonna say they're ordered like that. Now, in typical blockchains, and this is really the key concept, is the block time, the time that they have to build this block, do execution, which is here in blue, and consensus, which is here in green, is all shared within like T0 to T1, the block time. So typically they're doing this, selecting things out of the mempool, putting things in the block, executing in this blue segment here, and coming to consensus on it, all for block 1 in this time, right? And as you can tell, like the amount of time in this picture here for execution is relatively small, and that's actually drawn pretty much to scale. So in most blockchains today, like the time budget for execution is actually much smaller than the time budget for consensus here in green, because consensus takes a lot more time. These network messages across take the majority of time to actually add it to the blockchain. So the concept of asynchronous execution really only works when you have parallelism. So when you have parallelism, you do have multiple threads here. And so what we've done is we've taken that image of a single block with execution and consensus together, and we've exploded it in on the same timeline, but between 2 threads, right? And so here, again, execution is in blue, consensus is in green. And the difference here is because we have 2 threads, that block 0, the first block that validator was proposing, we can now spend all the time doing consensus, and in the next block time, we can actually execute the whole thing. So if you notice, this is the entire block time. And so the time budget for execution is now the entire block time. It's no longer just some small segment over here, right? And that translates directly to the gas limit of the block. So in this other scenario, you only had this small segment of the block as your gas limit. With asynchronous execution, because you have it on a separate thread here, now you have the entire block time to actually do execution, which means you just massively expanded your gas budget from some small section like that to here. This image is kind of cool because while it's a little bit harder to understand than what we showed on the other side, it actually pulls together like a lot of concepts that we talk about with Monad. Like we couldn't talk about this without talking about 2 threads. And so we see parallelism right here between both of these threads. You see pipelining between both of these threads in the sense that block 0 is doing consensus here in green, and then block 0 has execution done on it in blue here right afterwards. If you imagine time moving linearly like that, consensus is done first, execution is done second. And this separation on multiple threads is asynchronous execution. And so we see parallelism between the two threads. We see pipelining between the steps that they're doing on the threads. And we see asynchronous execution in the separation of consensus on one thread and execution on another thread. And it's really this combination of all these different things that make Monad such a performant system.